Welcome to this explainer. Today we're diving straight into the heavy lifting physics of getting a spacecraft off the ground. If you've ever found yourself wondering exactly how much energy it actually takes to defy gravity, well, you're in the right place. We're going to break down the grounded math behind orbital mechanics together, and it's absolutely fascinating. So here's our specific mission for today. We need to figure out the exact mathematical energy, or the total work required to launch a 1,000-kilogram satellite exactly 1,000 kilometers straight up into the sky. Now, I know it sounds like a standard, straightforward textbook problem, but as we're about to see, the universe definitely has a way of complicating things when you look closely. Let's actually visualize this journey for a second. We're starting right down here at the Earth's surface, point A, and traveling in a straight radial line all the way up to our orbital height at point B. This physical journey from A to B is exactly what we need to calculate the energy for. Now, looking at that straight shot up, you're probably thinking, can't we just use the old reliable formula from middle school? Work equals mass times gravity times height? It seems straightforward enough, right? Well, to see why that's actually a pretty dangerous assumption, let's quickly check out our flight plan. 1, the mission. 2, the trap. 3, harnessing universal gravitation. 4, the calculus solution. 5, the physicist shortcut. And finally, 6, reaching orbit. All right, number 1, the mission. Let's lay out the exact parameters we're working with here. We've got a satellite mass of exactly 1,000 kilograms. Our target height above the surface is 1,000 kilometers, which for our math translates to 1 million meters. Earth's radius is given as roughly 6,400 kilometers, or 6.4 times 10 to the 6th meters, and of course standard surface gravity is listed at a very familiar 9.8 meters per second squared. Which brings us to part 2, the trap. So here is exactly why that easy way fails us completely. That basic W equals mgh equation is great, but it relies on gravity being perfectly constant. Now that works fine at an everyday human scale, like lifting a box off the floor. But at a planetary scale, the pull of gravity actually weakens as you gain distance. To really put that into perspective, our destination is roughly 15% of Earth's entire radius away from the surface. We aren't just hopping off the ground, we are moving a massive fraction of our planet's size. That gravitational shift is simply too big to ignore. Honestly, if we just assumed gravity stayed a constant 9.8 all the way up, our math would be wildly totally inaccurate. Moving right along to part 3. Harnessing universal gravitation. To solve this mystery, we basically have to scale up our math and harness Newton's law of universal gravitation. Think about the r squared in the denominator of that equation. That inverse square law means that as distance increases, the gravitational pull drops off exponentially. Because of that, we literally have to reframe how we look at work. The work done by our rocket's thrusters must equal the total increase in the system's gravitational potential energy as that distance increases. We are essentially fighting a weakening but continuous invisible tether pulling us back to Earth's core. So how do we actually calculate this? That's part 4, the calculus solution. Since we're dealing with a dynamically changing force, simple multiplication just isn't going to cut it. We need to use calculus and integrate. First, we set our bounds from Earth's radius up to our final height. Next, we integrate the inverse square of the distance. And finally, we apply our physical limits to sum up all that required energy. And after applying those limits from point A to point B, we're left with this absolutely beautiful, if maybe slightly intimidating, algebraic expression for the total work done. It cleanly factors in the gravitational constant, the Earth's mass, the satellite's mass, and the difference in those inverse distances. Now for my favorite part, Section 5, the physicist's shortcut. Sure, we could plug in those giant messy numbers for the universal gravitational constant and Earth's mass right now, but there's an amazing insider secret. Because our mission data gracefully provided standard surface gravity at 9.8, we can use a really clever substitution. By swapping out that microscopic gravitational constant times Earth's mass for just everyday surface gravity times Earth's radius squared, we radically clean up the algebra. We're treating huge, messy constants for numbers that were already right there in our mission brief. Which finally brings us to part 6, reaching orbit. Let's bring it all home. First things first, we need to map our absolute distances from Earth's center, because in orbital mechanics, that is exactly where everything is measured from. Starting at the surface means we begin at 6.4 million meters. Arriving in orbit 1,000 kilometers up means our final destination is 7.4 million meters away from the center. Now for the fun part. We just drop those exact distances, the satellite's mass, and our handy gravity shortcut straight into our integrated formula. It literally transforms a daunting calculus problem into beautifully straightforward arithmetic. And crunching those numbers reveals our final answer. Lifting this satellite requires 8.4 times 10 to the 9th joules of work. That is 8.4 billion joules, an immense, almost dizzying amount of energy that perfectly quantifies the incredible feat of engineering it takes just to leave home. So we've successfully conquered the math for orbit today, but seeing this immense, mind-boggling energy requirement leaves us with a lingering question. If our basic everyday physics assumptions completely break down at just 1,000 kilometers up, what other comfortable assumptions absolutely shatter when we dare to look deeper into the cosmos?